This video is for section 32.4 of the book, talking about H-bridges. H-bridges are a fairly simple circuit. They are a generalization of the simple CMOS circuit we had, where we had two transistors, two field effect transistors in series, one of which was a PFET, that's the one up to the power supply, and one of which was an NFET. The two drains are connected together, and the two sources to the power supply and ground. That's the simple CMOS configuration we had before. For an H-bridge, we make two of these. And these are basically identical to each other. Except for this one's badly drawn. What we do is we take these two drains and connect them to either side of our load. What does this do for us? Well, what we can do is turn on only some of the transistors. Obviously, we don't want to turn on the NFET and the NFET and the PFET on the same side, because then we'd have shoot-through current directly from power supply to ground. But we can turn on the PFET on one side and the NFET on the other side, and then we have current flowing that way through the load. So this side would be positive, and this side would be the negative side for the load. We could also, or instead perhaps, turn on this NFET and this PFET, and now we're driving the current the other way through the load, with this side being plus and this side being minus. The advantage of this is that from a single power supply, so if this is, say, a 5-volt power supply, we can drive 5 volts across the load or minus 5 volts across the load. We do not need to have both a positive and a negative power supply. We can drive the power through the load in either direction. The cost is that we have two on resistances, both an NFET and a PFET, in series with the load, which means we need to make fairly large transistors so they have small on resistances so that most of the power goes to the load and not to heating up the transistors. Okay, how do we control this? That is to say, how do we get either the green path or the red path turned on? Let's take a look at the green path first. To turn on this NFET, we need a high gate-to-source voltage. Well, if we've got 5 volts as our power supply, well, 5 volts is going to be big enough to turn on our transistor. How do we turn off this PFET? Well, to turn off a PFET, you have to have the gate very close to the source, so put 5 volts on that one also. How do we turn on this PFET over here? Well, we need to have a large gate-to-source voltage, and remember, for a PFET, that's a large negative voltage. So taking this down to 0 volts, because it's a minus 5 volt gate-to-source, that turned on the transistor. And we need to turn off this this NFET, and so we need a very small gate-to-source voltage, and again, 0 volts will do it. And so what we end up having is that the two gates on the same side of the load are driven to the same voltage. Either they're both 5 volts or they're both 0 volts. Let's take a look at what it takes for the red path. It's the same reasoning as we had before, because there's a left-right symmetry here. To turn on this PFET, we need a large negative gate-to-source voltage, so we put the 0 volts there. To turn off this NFET, we need to have a very small gate-to-source voltage, so we put 0 volts on that. To turn off this PFET, we need a very small gate-to-source voltage, and so we bring that up to 5 volts. And to turn on this NFET, we need to have a large gate to source voltage, so we bring that up to 5 volts. And so all we've done is we've swapped which side has the 0 volts and which side has the 5 volts. The 0 volt side is the side that connects up to the power supply. The 5 volt side is the side that connects down to ground. And if you want to swap which one's connected to power, which one's connected to ground, you swap which one is the 0 volts and which one's the 5 volts. Okay, that's it for control. There's one other thing we need to worry about is what happens if we, say, turn off all the transistors, or what happens if we just switch between the two paths when there's an inductive load. When there's an inductive load, turning off transistors means that the current continues to flow and we're going to build up voltage on the node where things are turned off. So let's say we're running the red path here, and we just turn off those 2 transistors, not having turned on the green ones yet. Just turned off these 2. Well, what happens is that current continues to flow in that direction. This voltage will rise, this voltage will fall. Inductive spike. We had a solution for inductive spikes in a previous video where we put in a snubbing diode which went across the load. We can't really do a snubbing diode across the load here because we're driving the load in both directions. And if we've got a diode there, then one direction or the other, that diode is going to be forward biased and it'll take the current rather than the load. So we can't put a snubbing diode across the load here. But what we can do is have snubbing diodes on the legs of the H-bridge. So we can put a diode here, one here, and similarly one here, and one here. Now these diodes, if you notice, are all reverse biased as far as the 5 volts down to 0 volts. We're not going to get any current flow through them under normal conditions. But what happens with that inductive spike? When we turn off the red transistors here, this voltage goes up. When it goes up high enough, it'll turn on this diode and we'll have a place for that current to go. So this voltage could go, it was at close to 0 volts when the red path was on, it could go up to 5.7 volts. Similarly, this node over here, which was close to 5 volts when we started, can drop, and when it drops down to about minus 0.7 volts, that will turn on this diode, and we'll have the current that was flowing through here dissipated out to the power supply. And so the inductive spike here, the energy that was stored in the inductor has a place to go. It goes back into the power supply, basically charging up this, discharging this. It's going a little bit farther than the power supply normally likes to go. And so that extra energy that we're dumping into the power supply, it's a good idea to have a bypass capacitor that can keep that spike from propagating over the entire system. So we usually put next to each of these parts of the H-bridge, we usually have a bypass capacitor added. And that's to sort of contain the energy that was stored in the inductive load here. Of course, we don't have to rely entirely on the body diodes, because if we turn on, as we turn off the red path, we turn on the green path, then that load there, that current from the inductive load, still has a place to go, and we'll be rather quickly getting rid of that and building up the current in the other direction. So these diodes, sometimes we do add them, but if you remember from the schematic that we had of just an NFET, there was a body diode built into the power NFETs. That body diode is exactly what we need here to suppress the inductive spikes. So power NFETs have a built-in protection here against inductive spikes when we're building them into H-bridges. Those body diodes didn't help when we were doing just a single switching. So if we just had, an inductor to power and ground here, this body diode doesn't help much, because when we turned this transistor off, what happened is this voltage went up, and this diode becomes just more reverse biased. In that case, we had to add a diode in parallel with the inductor. But here, it's not the body diode of the transistor you're turning off that matters. It's the body diode of the other transistor here that is serving to suppress the inductive spike. So the fact that we have both an NFET and a PFET on each output here means that we always have a body diode in the correct direction to suppress either a positive or a negative inductive spike. These H-bridges are used extensively for controlling motors. We'll also be looking at another application of using them to drive a loudspeaker, because the H-bridge configuration is exactly the circuit that we'll be using for our Class D power amplifiers. And I think that is enough for this video.